Okay, the next speaker is Shijin Zhou on efficient retrieval of top similarity vectors.
Good afternoon, everyone. It's my pleasure to present my recent works on efficient retrieval of top similarity vectors. It is joint work with my colleagues at Baidu Research. So embedding vectors are common in modern machine learning and NLP systems. With the popularity of representation learning, such as word-to-vec, growth, fast text, gem, sim, Elmo, and BERT. Retrieval similarity word embeddings is a basic operation in natural language processing, such as synonym extraction, sentence alignment, and polysemous word learning. For example, when a user input a word and asks for a synonym, then both words, that means both words in the dictionary and the query will be embedded as a vector. It is a very fundamental task to find the nearest neighbor of that vector so that the algorithm can output the most similar word as the input query. And in my talk, I will focus on the measurement of inner product. So the retrieval vectors will be measured by inner product, and the task is what we call the maximum inner product search. Okay, here is a rigorous statement of our problem. We consider a subset of the Euclidean space, an arbitrary query from that space, and the data set on that space. That is the dictionary. For example, you can imagine that's all the words in the data set. N is quite large. And we also define a continuous binary symmetric matching function that maps from the space x times x to a real value to a scalar. You can imagine that is the score of similarity. Our goal is to find the optimizer of f, x, q, where q is the query and x is from the data set. In particular, we consider the inner product case. That is f xq equal to the inner product of x and q. We will dig out the trivial case. That is, we don't consider x is the trivial vector or the q is the trivial vector. And as you can see from this formula, we can, without loss generality, to assume q is a unit vector because only the direction of the query matters. It is worth to noting that this MIPS problem is equivalent to the weighted cosine problem. This is very critical in natural language processing. You can think of there is a weight, which means say the popularity of a word people will use in their paper or they would like to see. So you don't want to return a very real word when they search for the synonym. You can so there is a pair. Ci is the vector, and wi, you can imagine that's the norm of the vector, which measures the popularity of that word. So under this formula, if the word is embedded on a sphere, then via weight, we can find the weighted cosine distance in this way, which reduces to the MIPS problem. MIPS problem stands for the maximum inner product search problem. Okay, now I would like to introduce some previous work. The first one is the technique of acting a wrapper. We can increase the dimension and add a term where it is written as the square root of 1 minus the norm square divided by the largest norm. And for the query, we also need to add one dimension, that is a 0. If we do this transformation, then the problem will reduce to the cosine similarity case. And some other methods include range LSH, that is, LSH stands for locally sensitive hashing, phase PQ, greedy MIPS, and IP-NSW, which is a search on graph algorithm. Our approach is also based on the search on graph technique. Now I would like to introduce some definition, some math definition, but it should be very simple. First, I would like to introduce Voronoi cell. If a query drop into this region, Ri, then the vector we would like to return, the optimal vector would be xi, which corresponds to this Voronoi cell. It is very interesting that in the inner product case, not all the Voronoi cells are non-empty. That means given the data sets, we already know some of the vectors cannot be returned. If the vector in the data set has a non-empty Voronoi cell, then we call that an extreme point. However, recording these Voronoi cells are very expensive. So alternatively, people usually record the conjugate diagram, which is what we call the Delaunay graph. If the adjacency matrix, if the Voronoi cells are adjacent to each other, then we connect those two data points, so it forms the Delaunay graph. Our technique is based on the search on graph algorithm on this Delaunay graph. Now let's see what's Voronoi cells and Delaunay graph. The regions on this graph, on this plot, is the Voronoi cells, and the red dots corresponds to the data. Is the data points associated to the Voronoi cells, and the blue points are those data points without non-empty Voronoi cells. So the red dots are the extreme points, and it can be the optimal solution of the inner product search. And the Delaunay graph is the Delaunay graph is formed by the black edges. Okay, now I would like to introduce our algorithm very briefly. In the inner product case, given any query vector Q in the space, we start from an extreme point. We can randomly choose any extreme point. Then we move to its neighbor on the graph, which has a larger inner product with a query Q. We repeat this step until we get an extreme point such that it has an inner product that is larger than all its neighbors. Then we stop and return this point. If we have the exact Delaunay graph, then this local optimum will be the global optimum. This is proven by a previous work. Constructing the Delaunay graph is quite expensive, so in practice, we usually alternatively construct the HNSW. In HNSW, when we construct the L2 or cosine Delaunay graph, there is a criterion for choosing the edges. Let's see this case. Let's see this example. We consider the Q, and we want to select the neighbors of Q. A, B, and C are the nearest neighbors of Q. In the KN graph, Q, say 3NN, Q will be connected to all these three data points. However, in HNSW, we need to do an edge selection. If we choose all of them, not all of them are very good choices, because A and B has very similar directions. So instead, we will check this criterion whether distance of between Q and B is less than the distance between A and B, So that's not the case here, then we don't connect Q and B. We only connect A and C. We only connect QA and QC. This is a much efficient way to choose the neighbors. Unfortunately, in the inner product case, that doesn't work. So rather than using that criterion, we create a new criterion for inner product search. That is, the norm square of B should be greater than an existing neighbor A with the inner product with B. This means if the inner product itself is smaller than another existing neighbor, then we will not connect to that vector. That means we don't consider the B is a good representative of the neighbors. And empirically, this shows this is a much efficient way to construct the graph. Another contribution of our paper is a two-round construction. So at the beginning of the graph construction, relatively simple points are not true extreme points. Vectors coming in later may be vector candidates. So the solution is to exploit an additional round of graph construction to update the edges, especially for those nodes coming at the beginning. In this way, the graph construction algorithm can detect extreme points automatically. Okay, this is the algorithms in our paper. The highlights are the double round construction and the criteria of edge selection. For the rest of the details, I refer the readers to read our paper. So this is a visualization of our graph construction. On the left-hand side, that's the perfect anomaly graph. The middle one is our approach. The right one is the graph from the IPNSW. In the two-dimensional case, the denominator graph is quite simple, but we can still measure the efficiency of graph construction. As we can see, we can find the shape of the denominator graph. However, in the IPNSW, we can see that if we search on this graph, it is much less efficient. Now I will show the experimental result. We will do the tests on some data sets from natural language processing and some from the recommendation system. We'll compare with the methods of HNSW, hashing phase, greedy MIPS, and IPNSW. This is the plots of our result. The y-axis stands for the queries per second. That means how many queries we can process in a second. The x-axis is the accuracy or the recall. So if the curve is on the upper left corner, that will be the best one. As we can see in this 6 experiments, our method beats all the other methods. This is another experiment. It shows the percentage of inner product computation required among all the data points. So if the curve is on the lower right corner, that means the method is better. So in this experiment, we also show the better performance than other methods. So this is another measurement of graph construction compared with IPNSW. It compares the number of nodes with incoming edges. So if there is less nodes with incoming edges, that means we have already chosen some extreme points. So we can focus on only 10%. For example, in the first line, we can only focus on the 10% of the data points, while in IPNSW, they need to focus on 15%. So that will increase the efficiency. So let me summarize our work. So we propose a search on graph method, the inner product dynamic graph for maximum inner product search. It performs better than previous work, and also it is a better approximation of dynamic graphs. In this work, we focus on top 1 MIPS performance. For other performance, like the top-end inner product search, we also have another recent work focused on that. Okay, that's it. So any questions?
We have time for a few questions. Okay, maybe I can ask one. Do you think this method interacts at all with the kind of task you're evaluating on? For example, if you did this for document retrieval, would you expect different results?
Oh, that's an interesting question. First, we would also like to embed the documents into vectors. That also depends on how good the document embedding is. But I think in our work, we focus on sentence embedding and word embedding. That will be a very interesting experiment if we can also test on the document embedding.
Thanks. Okay, all right, let's thank the speaker again. And that concludes this session. Thanks.